name is Martina, Lessio, and I work in the chemistry department and in the group of Professor Emily Carter. I work on CO2 reduction to liquid fuels, and to explain in more details, my work focuses on finding materials or molecules that are able to take CO2 and convert it in something useful, like liquid fuels, which we really need for just energy production. And so this project has two really good aspects. The first one is taking CO2, which is a bad molecule that we want to get rid of, and we are producing in really large quantities. And the other side is to produce fuels that we need every day for any activity we do. So to get more specific, in this specific project, I work on a system that has been developed in the chemistry department by an experimental group, the group of Professor Bocarsi. And this system is really interesting to the scientific community because it does the process I described earlier, which is taking CO2 and converting it into liquid fuels, specifically to methanol, using a material called gallium phosphide, which is a semiconductor. So this material is able to absorb solar light, and then this solar light can be used to convert CO2 into methanol. So this process ideally will also use solar energy, so it will not require any kind of energy input. So again, another really good aspect of this kind of research. And also, this specific system is able to do this really well. So all the energy that this material collects is employed exclusively to produce methanol, and there are no byproducts, which is another really good thing from the chemistry perspective. And it also works really efficiently from, as I said, from the energy perspective, because we just use solar light and then apply a small potential. So a small energy input is required. And I'm a computational chemist, so I'm looking at this experimental system, and my contribution is trying to understand the chemical mechanism that the experimentalists are observing. And the reason we want to understand what the chemical mechanism is that if we understand the chemistry, then we can further improve this system. And of course, we do want to further improve this system because one day we want this to be a real application, something that we can use every day to reduce CO2 and produce energy. And so, as I said, I'm a computational chemistry, so I can use a number of tools to look at the mechanism of this behind this system. And this is described in this poster, where I went through several steps to check whether a previously proposed mechanism is correct. And with computational chemistry, I was able to find out that this previously proposed mechanism cannot happen because under experimental condition there is not enough energy for these mechanisms to happen. And so after realizing that, I then thought about other possible mechanisms that could occur, and I tested again with computational tools what's the energy required for these mechanisms to occur, and I found one that could actually occur under experimental conditions. So we ended up now with a hypothesis that is actually feasible under experimental condition, and now we are trying to move forward and trying to understand what's the next step.
Well, hey, thank you so much for talking with me. Really appreciate it.
You're welcome.